An important topic that we want to talk about is the relationship between finding the tangent line or normal line to parametric curves and use of the derivative. So derivatives and parametric equations. Suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve x equals to f of t and y equals to g of t. We also assume y is differentiable as well. Remember the chain rule. The rate of change of y with respect to a parameter like t is nothing but the rate of change of y with respect to x times the rate of change of x with respect to t. So we can basically divide both sides by dx dt and derive the following formula. dy dx, or the rate of change of y with respect to x, is equal to dy dt divided by dx dt, assuming the denominator is not 0. Now that we derive the derivative for dy dx, or the rate of change of y with respect to x, we can do the same thing and find the second derivative as well. To find the second derivative of y with respect to x is the derivative with respect to x of dy dx, which in turn can be written as the rate of change with respect to t of dy dx divided by the rate of change of x with respect to t. The first equation is used for tangent or normal lines, and the second equation is used for concavity. If this guy is positive, the graph concave up. If this guy is negative, the graph concave down, as we learned in elementary calculus. Let's take a look at one example. And remember that here we're going to use the point slope formula from algebra to find equation of tangent line. You have a curve like C, which is identified by parametric equations, x equals to t squared and y equals to t cubed minus 3t. Show that C has two tangents at the point 3 and 0. So 3 is your x and 0 is your y. Find the equation of the tangent lines as well. So first of all, when we are setting y equal to 0, we can take y and set it equal to 0 and find values for t. You have t cubed minus 3t, which is by the definition of parametric equations. If you factor out t, it becomes t squared minus 3, set it equal to 0, you get three values. T is 0, or t squared minus 3 is equal to 0, or t is plus minus square root of 3. Now, the rate of change of y with respect to x, by definition, is the rate of change of y with respect to t divided by the rate of change of x with respect to t, which in turns, on the numerator, you are taking the derivative of t cubed minus 3t, which is 3t squared minus 3, and on the denominator, as simple as that, the rate of change of x with respect to t is the derivative of t squared, or 2t. We can factor out 3 divided by 2, parentheses, you have t squared over t minus 1 over t, or t minus 1 over t, and you have 3 over 2 in front of it. So this gives us the rate of change of y with respect to x. If you plug in 0, this is undefined. We don't need it. So we just need to plug in plus minus square root of 3 to find m, or the slope of the line. When you plug in plus minus square root of 3 into this formula, you get 3 halves times square root of 3 minus 1 over square root of 3. You can take the common denominator between them, simplify this, and the rate of change becomes plus minus square root of 3 for these two values. So as you can see, we expect to see more than one tangent. Here we have two tangents. Later on, I'll show you the graph and you see why we expect to have more than one tangent. So the equation of tangent lines at 3 and 0, following the point slope formula, which is y minus y sub 1 equals to m times x minus x sub 1. Here, your y is equal to 0, so this guy becomes just 0, y is equal to square root of 3 times x minus 3, and y is equal to negative square root of 3 times x minus 3. So you have two tangents at this point. If we change the point, you might get different tangent lines. Let us go back to the exact same parametric equations. Question says find the points on the curve where the tangent is horizontal or the tangent is vertical. This is the visualization of the graph. This curve doesn't represent a function because it doesn't pass vertical line tests. And at the point 3 and 0, as we saw, we have two tangent lines. One of them is increasing because m is positive, and the other one is decreasing because m is negative. Okay, as you can see by the visualization, we expect to see two parallel lines where you have flat tangent lines. So you have horizontal or flat tangent line. And we expect to have a vertical tangent line around here. So let us do the algebra. C has a horizontal tangent when the rate of change is equal to 0. So you just need to take the numerator and set it equal to 0. Remember the chain rule that we defined and we use for dy dx? On the numerator, it has dy over dt. You only need to take the derivative of y with respect to t and set it equal to 0. Okay, dy dt is equal to 3t squared minus 3. And if you set this guy equal to 0, t squared minus 1 is 0, or t becomes plus minus 1. Okay, when t is equal to 1 and t equals to negative 1, we expect to have horizontal tangent. When t is equal to positive 1, x is 1, and y becomes 1 minus 3, or negative 2. When t is equal to negative 1, x is again 1, but t becomes negative 1 plus 3, or 2. That's how you end up with these 2 points. The corresponding points on C are 1 and negative 2, 1 and 2. Well, C has a vertical tangent where the denominator is equal to 0. So when dx dt is equal to 0, it means that t is equal to 0. So when t is equal to 0, x becomes 0, y becomes 0. At this point, at the origin, we have a vertical tangent. So the corresponding point where you have a vertical tangent is just one point, which is your origin. Let us move on to concavity. How do we use the second derivative to analyze the concavity of the graph? Determine whether the curve is concave up or it concave down. To determine if you have concavity, you need to check the second derivative. First of all, remember the first derivative. This is the formula that we derived for the first derivative. The formula for the second derivative says, hey, we need to take the derivative of y with respect to x with respect to t, set it on the numerator. On the denominator, we need the derivative of x with respect to t. This is not difficult. 3/2 stay the same. The derivative of t is just 1. And the derivative of negative 1 over t becomes positive 1 over t squared because you end up with two negative signs. On the denominator, the derivative of x with respect to t, which is t squared, becomes 2t. If you simplify this using algebra, you get 3 times t squared plus 1 divided by 4 t cubed. Here we take common denominator, and then we multiply 2 and 2. We multiply t squared and t. And this is the formula for our second derivative. What is important here is t squared plus 1 is always positive. So it doesn't have any role in the sign of this fraction. The only important part is t cubed that determines the positivity or negativity of the second derivative. This is important. So obviously, the curve concave up when the second derivative is positive. When the second derivative is positive, it means that t must be positive. When t is positive, your numerator is always positive, so the fraction becomes positive. The curve concave down when t is negative. When t is negative, the whole fraction becomes negative. You can check it here in the graph as well. When t is negative, you have concavity, which is downward. When t is positive, you have upward concavity. And all based on the sign of the second derivative of your curve. Okay, we use the first derivative, we use the second derivative. Let us move on to another example. Find the tangent to the cycloid x equals to r times theta minus sine theta, and y is r times 1 minus cosine theta at the point where theta is pi over 3. Okay, when you're talking about tangent, you're talking about the first derivative. We need to find the slope of the tangent line. To do that, we need to find the rate of change of y with respect to x, which is the rate of change of y with respect to t, divided by the rate of change of x with respect to t, or theta in this case. The rate of change of y with respect to theta is very simple. You have r times the derivative of 1 is 0. The derivative of negative cosine of theta becomes positive sine of theta. On the denominator, we have to take the derivative of x with respect to theta, which is nothing but r. The derivative of theta is 1 minus the derivative of sine, which is cosine. You can cancel out r and r. We end up with sine theta divided by 1 minus cosine theta. Very well. So when theta is equal to pi over 3, our x and y values are x is r times pi over 3 minus sine of pi over 3. Just take a look at this. We just use a simple plug-in. But at the same time, from pre-calculus, you know that sine of pi over 3 is square root of 3 divided by 2. Now for your y. Y is r times 1 minus cosine of pi over 3. But cosine of pi over 3 is just a half. So 1 minus a half is just a half. You end up with r divided by 2. Okay, we have our x, we have our y, we need the slope. dy dx is simply sine of pi over 3 divided by 1 minus cosine of pi over 3. This is dy dx. After simplification, you get square root of 3. So we expect to have an increasing tangent. Very good. So take a look. The slope of the tangent is positive. It is square root of 3. The equation is a little bit complicated, but it's because we have r. Y minus r divided by 2, which is your y sub 1 equals to m times x minus x sub 1. You can simplify this further, or you can leave it as it is. The visualization of the cycloid is as follows. Here you see the graph repeats itself, and it has horizontal tangent, and at theta equals to pi over 3, you have an increasing tangent with the given equation. So this is the equation of your tangent line to this parametric equation as we discussed in this lecture.